Alright, so we're going to go ahead and do a video here on Newtonian gravity, not the Einstein relativity type gravity, but the Newtonian one. And we're going to start by going over Kepler's laws. There are three of them. These are his laws of planetary motion. The first law is that planets move, and I'm not going to write this all out, but planets move in ellipses. Let's pretend that's a nice ellipse. And they move in elliptical orbits. So here's our planet going around in this elliptical orbit with the sun at one focus. So we'll have two foci on an ellipse, and the sun would be at one of them. In our solar system, most of the orbits are really circular, such that the foci are really like right next to each other. And so the sun is at one of the foci, but it's right real close, and so it's we're going to do a lot of the approximations of all of our orbits as circulars because it's a lot easier than doing elliptical, and most of them are closer to circular like this than they are elliptical. And circles are ellipses anyway because they're just ellipses where the two foci are at one point. The second law is that in this elliptical orbit, I guess I'll draw one more elliptical orbit, right? Here's our elliptical orbit, that a planet sweeps out equal area in equal time. So what they mean by that is if we have our planet here and we draw a line back to the sun, the focus that the sun is at, and then we wait something like, it could be any amount of time, but let's say we wait a month, it'll sweep out and cut out this kind of like wedge, let's say. So it's this area that it sweeps out here, right? Let's call this one, area 1. And let's say that this was in some time t. We'll call this area 1. If we look at that same amount of time at any other time of the year, like say the planet is here, what you'll find is that this wedge shape, this slice of pizza shape that's cut out, right? And it's that same time. If these two amount of times that passed are equal, then you'll get A1 equals A2. They will equal each other. And this is basically a statement of conservation of angular momentum. What that means is that over here on this side of the ellipse, when it's closer to the sun, the planet is actually moving faster. So it's closer and faster, kind of like a figure skater tucks their arms in and they start spinning a lot faster. So as it gets closer to the sun, it's going on this smaller curve here. It goes faster, so it travels a bigger distance, and you get a wide, short slice in that amount of time. When it's out on this end, when it's further away, you get a shorter distance here. So this is further and faster. I'm sorry, not and faster, and slower. It's further and slower. You get a shorter distance traveled here during that time, but you get a much longer slice here. So it's like a skinny long slice, but it'll basically work out so that these are the same. So it doesn't matter if you look over a month. I think I said a month. It could be 5 months, 6 months, or a day or whatever. It sweeps out equal area in equal time. In other words, it has a constant areal velocity, that the area it's sweeping out per unit time instead of just the distance it's covering per unit time is constant. Okay, and his third law states that the period of an orbit is directly proportional to its distance from the sun cubed, especially if we're working in circular motion. So if you think about this, if we've got a circular path, then gravity is the centripetal force, which means we can take and say that G, mass of the sun, mass of the planet, over r squared, that would be the force of gravity. I guess I should probably tell you this. This is the force due to gravity, Newton's gravity, mass 1 times mass 2 over r squared. I'm sure we've seen it before. This is the universal gravitational constant. This is the mass of one object. This is the mass of the other. And here is the distance between their centers squared, much like Coulomb's law here. And so constant, two masses, distance squared. We're going to use this capital M as the mass of the sun, this lowercase m as the mass of our planet. And since it's going in a circular orbit, in this case, we're looking at a planet orbit here, we can set this equal to r mv squared over r, centripetal force. This means that the masses will cancel, right? And then we've got mv squared over r and we have this r squared here, which means we can cancel that r and cancel one of those. And we've got gm over r equals v squared. But remember, v is equal to omega r. So we're going to replace this with omega squared r squared. Now we can multiply this r over and we'll get an r cubed here, right? And we have gm, which is just going to be a constant. The mass of the sun's not really changing. This constant stays the same. We have omega squared, and remember, omega equals 2 pi f, which equals 2 pi over the period, which means we can write in 4 pi squared r cubed over t squared, gm is equal to gm, and then just with a little rearranging you get that the period, multiply the period over, is equal to 4 pi squared over gm. This part is just a constant, and then r cubed. And there you go. I'm sorry, this was t squared. We've got our relationship here that tells us that t squared is proportional to r cubed. So that was kind of a proof of Kepler's law using Newtonian gravity. In fact, Newton went through and used this equation for gravity and showed and explained all three of Kepler's laws using it. So there was our first use of the force of gravity there. I maybe jumped a little early on that before I actually explained it, but we'll get into that now. So again, we're only interested in circular motion, so now let's actually talk about this equation that I was just using. This is Newton's universal law of gravitation. So, you know, Newton's universal law of gravitation, sometimes you put a little sub g. Capital G, mass 1, mass 2 over the distance between their centers squared. G is the gravitational constant. It's our constant of proportionality, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That right there is the value for that. It always stays the same. It's a constant. And then this is our regular old equation. Now this is the distance between two centers. So if we have a star or a planet or something here and another one here, that distance r is between their centers. Technically this is only for point masses, for each individual mass, but when things are spherical, you can treat them as though they're a point mass at the center. So that would be r, this would be m1, this would be m2, and then you could plug it in and find out what the force of gravity would be between them. This is most definitely a vector, so if we had something like this and we wanted to know the force on mass 1, we'd do this equation with that. And if there was another mass, say another mass over here, m3, and we wanted to know the total mass, the total force, we could call this R2 and this one R1, you have to then do the force between M1 and M2, the force between M1 and M3, and then do the vector sum of the two. You have to then add them up. The force of gravity is always attractive. We've not found a repulsive a force of gravity. There seems to be a little bit of evidence now. There might be some anti-gravitational force with that whole dark energy thing, but basically if you hear the physicist say the word dark, it basically means he doesn't know. So that kind of should go there for you. So kind of keep this in mind. Remember, this is an r squared here. This is because of the spherical symmetry. If this sends out a certain amount of gravity as it goes out on a larger and larger sphere, it spreads out, the strength of that gravitational field spreads out over a larger and larger sphere. And remember that the area of a sphere is 4 pi r squared, and we just take that 4 pi and it's absorbed into g, and we have just that r squared. But the 4 pi was in there. I don't think it was realized by Newton that it was in there, but it basically is in there. It's just part of this constant now because 4 pi is a constant. So you end up with this 1 over the surface area of the sphere, and as you get further away, it degrades with that spherical symmetry that we're looking at. Next thing we can do is talk about actually drawing a gravitational field. And so we can come along just like we did in electricity and magnetism in the past, if you've ever done it. You have that electric field. And the basic idea is to look at some planet. Let's say we have some planet or sun or star or something like that. And what we're going to do is we're going to want to put a tiny little mass near it, something so small that the planet or star or whatever doesn't notice. And then what we can do is we can say, all right, we can measure the force on the test charge is equal to g, the mass of the star or planet or whatever, times the test mass, this tiny little mass, over their separation squared. So, you know, this distance here, r, right? And then this is so small that if that thing is there or it's not, the star doesn't notice, it's not going to move the star or anything. We put it there, we let it see how much force is acting on it, and then we divide it out. So we divide out the test charge on both sides. And then what we're left with is a force per unit mass is equal to g m over r squared. And then if you look at this, we can just take whatever number this happens to be. Let's call it, let's just call it a lowercase g for now. We'll call this our gravitational field. That I'm going to rewrite it one more time here. G equals g m over r squared. We can basically just take this g number, multiply it by whatever mass now we put. We come back in and we put some bigger mass at that part, whatever m happens to be, multiply it by this g, and it's just going to add that m back on. So this is our equation, but we come in, we put this mass right there now in that place. We come in and multiply it onto this g, and we're multiplying here, and we're right back up to this equation here for the force, and mg will give us then the force on it. Now if you see this m times lowercase g and it looks familiar, it should, because that's the equation we used for weight. And if you look at this, notice I also used g. If you look at this, this is a force per unit mass. Well, what unit is that? That's a Newton per kilogram, right? Which is then, so that's our unit for our gravitational field. A Newton per kilogram is a kilogram meter per second squared divided by a kilogram, because that's what a Newton is. Well, the kilograms cancel and we're left with meters per second squared. So this is an acceleration. Our gravitational field is the acceleration that would be caused on an object if we put it at that point in the gravitational field. So gravitational field, this is gravitational field, and it is equivalent to the acceleration that would be experienced by an object put at that spot in the gravitational field. Okay, so as you can see, this mg is just the force. So we get right back to that Fg equals mg, which is what we were using before. All right, this was our weight. We can also draw these fields. So let's say we had a planet or something, or a star or something big and heavy here, and these are all attractive forces. We can just draw a gravitational field in this way. The reason we draw it this way is because we don't want to go through and draw a bunch of vectors everywhere. When we do electric fields, this will get explained a lot more, but quick courses, the gravitational fields point into the masses, and then they are, because they're attractive, and then the further apart the lines, none of the lines cross, and the further apart the lines are, the weaker the force is. So if you look here, the lines are this far apart, and it's stronger as you're near. As you get further away, these lines spread out, indicating it gets weaker. Otherwise, you'd have to draw a vector pointing inward at every single point here, and it would just become a giant mess. So we just use those couple of rules just real quick. It gets weaker as you get further out, but this is essentially the only picture you have to draw for gravitational field, so we'll worry about writing out and doing these field lines more formally. We'll leave that for doing electric fields. All right, last part of this is orbital motion. Okay, let's go through orbital motion. And basically, we are treating things as though they are circular orbits. So, circular orbits, that's what we're interested in, and all our orbits here are close enough to that we can treat it as that. Again, it's mv squared over r, this is what we did above to get Kepler's third law, is equal to the force of gravity, m over r squared. So little m is the mass of the orbiting object, big M is the mass of the central object that's being orbited. The masses cancel, one of the r's cancel, and you're left with then taking the square root. V equals the square root, right, because we want to get rid of that square, g m, that's the capital M, m over r. Okay, and this is actually the tangential velocity. So if here's our big central object, right? That's the capital M. Here's our little m, and this would be its tangent velocity at any moment. We can just use that. We can just use the idea that gravity is a centripetal force. It's making this accelerate toward the center. So we have a centripetal acceleration, and therefore we can just come up with this tangential velocity right there. Okay, I think that's pretty much everything for gravitation. Just make sure you remember how to draw these fields. Remember how to just kind of derive these. It's mostly just from using centripetal force and Newton's law of gravity, and then of course finding the force between these things. Don't forget it adds like a vector. So like if we did this here, if we wanted like the net force on mass 1, it would be the force of 2 on 1 plus the force of mass 3 on 1. And it's a vector sum. So you have to go in and, say, oh, this vector's pointed this way, and this vector's pointed, this vector's pointed this way, and this vector's pointed this way, and then you have to put them tail to tip, and you have to break them into components, and then find the big right triangle and add them up. So you have to do all that, and if there's 3 or 4 or 5 or however many of them there are, you do that superposition of them and add them up like vectors. Okay, I think that is now actually everything. All right.